Welcome back, physics students. If all is going well and you're following the schedule, this is the first lab that you will be assigned the air tract. So I wanted to make this introductory video just to briefly explain what the air tract is, how measurements are collected, and more importantly, how I'm going to pass that data along to you for you to do your analysis. And you'll find that I'm going to make it easy for you. So with that said, the air tracts. They are about 8 feet long. They operate with the same concept of that as an air hockey table. A shot vac is connected to the track. It pumps air through the track, and there are little holes on top of the track that the air escapes from, and it elevates the rider that is on top of it, so we eliminate friction. There is a little wire sticking out of the rider, and it is held at a different potential than the actual track, and sparks are emitted at regularly spaced intervals at your choosing, so that a spark is emitted and it goes from the wire to the track. And the significance of that is that there is a long piece of tape, thermal tape sandwiched in between the wire, or your lab manual calls it a whisker in some cases. And the spark goes through that paper and it makes a little dot. So we have a precise record of where your rider was at any given instant of time. What you have to do is get that long ribbon, put it on your desk, put a 2-meter stick up against it, and measure out those dots as carefully as possible. So how am I going to collect this data and pass it along to you? What I suppose I could do is do some test runs, get that ribbon, and cut it into like little 10-inch segments, and let's say we end up with 5 or 6. I could take those to a regular sheet of paper, scan it, and send it to you. But beforehand, I suppose I'd have to darken the marks because they're pretty light. They probably wouldn't show up. Have to do that meticulously for each dot so that I don't introduce any error. Then you have to measure from the reference point on the first segment to a dot, then the second, third, fourth, fifth, sixth, seventh, and then the next segment. But on the next segment, when you come across a given dot, the total distance the cart traveled would be the distance from that dot to the edge of that paper plus the length of the original segment, and so on and so forth as you go down the row of ticker tape segments. That's a lot of work. You're introducing more error. I got a better way for you to do this lab, and this is what we're going to do, provided that your instructor agrees that this is acceptable, which I suppose if you're watching this video, they have. We're going to use the Pasco Smart Card. Now, with the Pasco Smart Card, the position of this cart that has wheels on it that I'm going to roll across this track is connected to some software. So that software acquires data that gives me the position of the cart at any given instant of time. So no measurements you have to do. With the ruler anyway, I am going to give you those measurements. Now, if you were making these measurements with a ruler, in a lot of labs you do need to report the uncertainty in your measurements. So with the ruler, you'd have some error associated with those measurements. For this system, there's error as well, just like with anything, and I will report that value to you. In fact, I could do it now. It's 0.001 meter. That is the error associated with each position that you will be given. Now, let me put you on pause and give you a quick demonstration. So here is an overhead view of the track sitting on top of my desk. There is a Pasco Smart Card on it. I'm going to give it a push, and there it goes back and forth. Now let me put you on pause and let's take a look at the data. Okay, let's take a look at a small segment of some of that data that was collected. I plotted position versus time, and this here shows each data point of the collected data. During this segment here, the cart was traveling down the track. Right here, it collided with its edge, ricocheted, went in the other direction, reached the edge of the track, ricocheted, went in the other direction, so on and so forth. With this software, we can do other things. Well, we can do a lot of things. What is of interest to you would be, let's see, there's one lab where actually you get to use this software and you're required to plot velocity and time. So here's that curve for this particular data set. along this time range here, 0 to 6 seconds. I had hit record, but I hadn't touched the cart yet, so it's motionless. My finger was on the cart during this segment here. During this segment, it was traveling along the length of the track, collides with the edge, goes in the opposite direction, and so on. You are going to use this software only in 2100. And in that case, if you're asked to generate velocity versus time, I would simply give you this graph. So for most labs that involve this, that involve the air tracks, you are going to make graphs like this one here, the position versus time. So obviously I wouldn't give you this graph, right? You're supposed to generate it. What I would do is I would pretend that you received the ticker tape, you measured out those dots, and give you a table like this. So this table lists the data points. Again, we're pretending that you took this from a ticker tape. So 1 is the first point, 2 is the second point, 3 is the third, and so on. And these are the positions of those points on that ticker tape. And let's see, I think I told you in the beginning of the video that there was an error of plus or minus 0.001 meter. I stand corrected. When we do the actual experiment, I will remind you. I will check on the exact error, but looking at these numbers, it looks like it's 0.0001 meter of error. Let's see. I was browsing through the lab manual, and it looks like they give you a table where you're supposed to fill out the time that corresponds to this position and this one, and this one. Well, all of them. Like, in other words, at what time was your rider at 0.2589 meters? And I'm almost tempted to give you a table that just looks like this. See how it already has the time values? But, well, you're supposed to do it yourself. So the table you get will just be a list of data points and the positions. I mean, this is trivial anyway to determine at what time these events occurred. All you need is the frequency of collected data, which will be provided to you in your, excuse me, in your, let's see, in your lab. I think the frequency is like 10 in one lab. But we're going to have a different frequency with these passcode cards so that we have a large number of data points that cover a small range of motion so that we can neglect the effects of friction. But I'll give you that frequency. So I hope you found this helpful, and I hope I didn't confuse you with, talking about frequency, but once you read your lab manual, it will be clear as a bell what I mean by that. This here is what I will provide you with. So it's like I'm doing the measurements on that ticker tape for you. And with that, let's get on to our experiment. All right, 2100, let's go. This is accelerated motion on a track. What your lab manual wants you to do is let a rider roll down an incline, collect the data, make a graph, determine the slope to figure its acceleration, and then do it in the opposite direction. Let it roll up a ramp and collect the data, make the graph so that you can determine its acceleration and average the two. Now, let me say something about this particular cart. I just discovered that there's this preference for a particular direction. When it's moving from your left to right, the acceleration is a bit slower than it should be. And then when it moves in this direction, it's a bit larger than what it should be. Now, I could move these risers to the other side and do the experiment with that side of the track raised, but I'll still get the same results when it goes this way. the acceleration is slightly less than what it should be. When it goes this way, it's slightly larger. I can also reverse the direction of the cart and do the experiment again, and then move these back to the other side and reverse the cart. I've tried it all, and I'm dead set on finding out why there's a preference, but that doesn't matter. Clever authors that they were, the way they wrote your lab manual is to take those factors into consideration. We are going to, well, that is why we're going to roll it once up and then one down the track and average those two accelerations that we come up with. So what you're supposed to do is 2 separate runs. Now with this, we're just going to do 1 run. Why not? With the air track, you're limited to 1 run at a time, right? Because it's making those sparks on the ticker tape. You can't let it roll down a track, click, 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 making those marks, and then let it roll back up, click, 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 making marks again on that same segment of tape, because they'll be superimposed on each other. But that's not an issue with the smart card. It's on the track, and I'm recording data. So 2100, we've just done the experiment. Actually, let me put you on pause and show you some of the results. So here's a record of your data, and I suppose I can go over it, but you saw the video, you can make sense of this. For instance, from 0 to 6 seconds, we have a flat line because the cart was indeed stationary. There was no motion. This is the area of interest. Right here, it collided with the bumper at the end of the track, and it went up and down again, collided, went up, and then I took the car off the track. What I'm going to do is I'll send you this data right here. Now, according to your lab manual, since you have 2 runs, they want you to make 2 graphs. You can still do 2 graphs if you like. One when the cart is going up, one when it's going down. Here's the up part, here's the down part. Or if it's okay with your instructor, you can just make 1 graph and find the slope of that line. In either case, you will be averaging all of those data points to get 1 acceleration. Maybe perhaps you want to just stick with the way they asked you to do it in your lab manual. By the way the Spark timer is set up in the lab, it is recording data points with 0.1 second intervals. If you'll notice, we have a frequency of 20 hertz. I chose that frequency so that I would indeed get approximately 20 data points for the motion going up and 20 for it going down, which the lab manual asks for. So I have it on a frequency of 20, and that means nothing more than in the span of 1 second, the software measured the position of the cart 20 times. So you should be able to figure out from that what the time interval is between 2 points. And I'll send you a table that looks something like this. You'll have your data points numbered, and they will pertain to the cart's position. I won't send you this, of course. We're not interested in these points. This is when the cart was at rest. I want to send you these highlighted areas, so you'll have a good set of enough points to make your 2 graphs. Now I'm going to put you on pause because you need 2 more measurements to complete your analysis. So I'll be back shortly. So what you need to do now is figure out your H and your L measurements, and that's used to determine the slope of this incline here. Now, right after this segment of the video, I'm going to insert another segment that fully explains how you're gonna do that, but I wanted to say something before I sent you that, because I already recorded it, and technically when I recorded it, it was for physics 1570. Now 1570 does something like this, and you're gonna do the same measurements as they did, but they have their own vernier caliper. Yours is more accurate. It gives you an extra digit, and there's another difference between yours and theirs. Their caliper has the centimeter scale on the bottom and the inches on the top. So in that video, I stress, hey, use the correct scale, the one on the bottom. But for yours, 2100, you're gonna use the one on the top. So disregard that comment that I make. I'm going to send you pictures of measurements with the vernier caliper that you have already used previously in this lab to make it consistent. So let me show you that video now. So what you need to do is measure L and H. The L would be the distance between the feet. So what I did was tip this upside down and unscrew the feet so that I could see the holes that these feet screw into. I mean, I could have done it a different way, but without going into it, I think this is the most accurate. On the chalkboard here, you'll see a diagram. Let's say these represent the holes, and you wanted to measure the distance between those two holes. So obviously it's center to center. That's what your L is. A more convenient way would be like measure that edge and this edge. So what I will do is get a meter stick and place it between those two holes and photograph this for you. I'll put the camera overhead so that you could see the initial position of your measurement, and then take a photo overhead of this screw hole, and you can get your final position. And when I place this meter stick on the track, I'm not gonna like adjust it so that one end is like perfectly at 0 or anything like that. I mean, this is your job to determine what the L is. I'm going to place this at an arbitrary position. I mean, it'll for sure be right across the diameter of the screw hole, but it'll be up to you to get the best measurement for L as you can. And I'll put that lens right over the edge so you can get an accurate reading based on a photo. So that's how you get your L. For your H, we use these risers. There's 2 here, one for each foot on the left side of the track. So for your H, all you need is this length here. And to make that measurement, we're going to use a vernier caliper. And I'll send you a photo of that. Let's see. I made sure I used the same type of caliper that is illustrated in your lab manual. Your lab manual does a pretty good job of explaining how to use one. So I used the same type that they used. I took a picture of the of this in the caliper's jaws. Then I zoomed in on the scale so you can get an accurate reading. And for this, let me think. There's 2 scales. One is in inches, one is in centimeters. We never want to use inches, right? The centimeter scale is the scale on the bottom of the caliper. So just keep that in mind that you are looking at the right scale. So let's see, let me just go over it in my head real quick. You have enough information to get the height that we raised one edge. You have the data to determine the length of the base. That'll give you the slope of the we're all set. I erased it, but you had the frequency of these acquired data points. You have the error associated with those data points. Oh, so there obviously is also going to be error in your reading with the meter stick and with the vernier caliper. That, I'll leave that up to you. There's inherent error in those instruments and how you read them, and that should be explained in your lab manual. But another quick one, I will see you next week.